Okay, we can start, and the other students, they can join us. Let me first share my file. I hope you already study these problems, the tutorial for this week. We have the first problem. We have a lever with length, the 12-pound lever, and with a 10-inch radius of gyration about 0.0. So the radius of gyration about this point, the fixed point of the rotation, is 10 inch, is initially at rest in the vertical position, where the attached spring of a stiffness K is equal to 3 pound per inch. This is the stiffness of the spring, is unstretched. So when theta is equal to 90 degree, or pi divided by 2, the spring is unstretched. When theta is equal to 90 degree, this lever is in vertical position and the spring is unstretched. So calculate the constant moment M applied to the lever through its shaft at O, which will give the lever an angular velocity of 4 radian per second. As the lever reaches the horizontal position, theta is equal to 0. So this lever, we want to calculate the moment M, which is applied to this lever. We should obtain the value for M, which when theta is equal to 0 and the lever is in horizontal position, I mean the final position, if we assume that this is the final position and the position of G will be some point here, we want to have an angular velocity of 4 radian per second. So for this purpose, we can write the energy and work equation here, because we have a spring and also we have one external moment M. The best option for this type of problems is using the energy and work equation. So if we write the work equation, we will have the work from position 1 to position 2 is equal to M times by theta. Here we have the external force is M. In fact, this is the moment. The work done by M is equal to M times by theta, which theta during position 1 to position 2, which is from theta is equal to pi over 2 to theta is equal to 0. So W1 to 2 is pi times by M over 2. The initial kinetic energy is equal to 0 because it starts from rest. The final kinetic energy is equal to half I/O omega squared. You know, this is a rigid body because this is a pure rotation about 0.0. So we can write the kinetic energy is equal to half times by the mass moment of inertia about the fixed 0.0 times by omega squared. So this is the T2. And IO, which is equal to the mass times by radius of gyration squared. The mass is 12 pounds, so it should be here. This is 12 pounds. So we divided the mass by 32.2. This is the mass times by K squared, which K is the radius of gyration. Here, this is the radius of gyration, 10 squared. So this is the IO. Now we can calculate that the final kinetic energy is equal to half I/O omega squared, and the omega, it must be 4 radian per second. So the final value for the kinetic energy at theta is equal to 0 is 298.13. So now we need to obtain the potential energy. We know that the potential energy in initial condition is the potential energy of gravity and the potential energy of the spring. In the initial condition, if we assume for the gravity, we need to obtain one datum level. We assume that this is the datum level. So in the initial condition, when theta is equal to 90 degree, the position of point G is 8" upper than the datum level. So it will be W times by H, which H is 8. This is the initial gravity potential energy. The spring potential energy due to the spring is equal to 0 because we know when theta is equal to 90 degree, the spring is unstretched according to the problem description here. So here, this is the attached spring of stiffness K3 is unstretched. So according to these sentences, we can conclude that potential energy of the spring is equal to 0, and we only have the gravitational potential energy, which is 96 pound-inch. And U2, or the final potential energy, is equal to, again, the gravity potential energy, the potential energy due to the spring. And in the second position, or in final position, when this lever is in horizontal position, it means that the mass center is located on the datum level. So you can see here we have 0 for the gravitational potential energy. But for the elastic potential energy, we have half kx squared, which we need to calculate the x. When this leverage is in a horizontal position, the length of the spring is 15 plus 15. Here we have 115 and another one is here. So the length of the spring will be 30" and it should be here. This is the 30 minus x naught, which x naught is the initial or unstretched length of the spring. And x naught, the unstretched length, is equal to a square root of 15 squared plus 15 squared, because when this spring is in vertical position, the length of the spring is the unstretched length. And according to the trigonometry relations and Sygros relation, we can conclude that the length of the spring is equal to 15 square root of 15 squared plus 15 squared. So this is x naught, and we can substitute and calculate the final potential energy. Now we can substitute into the equation for work and energy and simplify this equation to extract the value for m, and m will be 202.4 pound-inch. Okay, is it clear? Any question? No question? Okay, we continue with the second problem. Each of the two hinges at A and B of the uniform lead of mass m of a child's toy chest contains a torsional spring which exerts a resisting moment m is equal to k theta on the lid as it is being closed. Specify the torsional stiffness k of each spring, which will result in zero angular velocity of the lid as it reaches the horizontal closed position. When released from rest at theta is equal to 0. And part B, what would be the angular acceleration alpha of the lid when it is released from rest in the closed position? So we want to calculate the required K in this equation. When we release this lid from theta is equal to 0, we want to calculate the K in a way that when it reaches to the theta is equal to 90 degree, again the velocity of the lead must be equal to 0. So we will have theta 1 is equal to 0 again because the lead will be released from the rest. The final position kinetic energy is again 0 because we want to calculate K in the way that when the lead is in theta equal to 90-degree position, again the velocity must be equal to 0. So the kinetic energy must be equal to 0. The initial potential energy when the lead is in a vertical position or in theta is equal to 0 position. So if we assume that this is the datum level, so it will be mgl divided by 2, which L is the length of the lead, and the position of the mass center for the lead is exactly at the center of this lead. So it will be mgl divided by 2. V2, or the position, the final position potential energy, which is the energy stored in the springs. We have two springs at A and B. Each of them has uh, has exerted a moment of k theta. So the energy stored in this spring is equal to the integral of k theta d theta, okay, from 0 to pi divided by 2, and we have a coefficient of 2 because we have two springs. So in this equation, if we calculate this, the integral of theta d theta is theta squared divided by 2, which the 2 is cancelled out with this 2. So we will have k theta squared from 0 to pi over 2. So this term is the potential energy in the final position, pi squared divided by 4 times by k. Now we can substitute this value into the energy and work equation, because the work done by the external forces is 0 because there is no external forces. Only we have the force exerted by these springs and also the weight, which both of them will considered in the potential energy. So if you substitute here, this term is 0, T1 is 0, and T2 again is 0. So we only have V1 and V2, or the potential energy in initial and final position. So from this equation, we can conclude that K must be equal to 2 times by mgl divided by pi squared. So if K was equal to this value, and you release the door from the position of theta is equal to 0, or the vertical position, the door will come down, and the velocity, the angular velocity of the door, again when theta is equal to pi over 2, or the door is in horizontal condition, again the velocity will be 0. Now in the part B, we want to imagine that we release the door with the same spring with this stiffness. We release the door from the position of theta is equal to 90-degree. We want to calculate the angular acceleration of the door exactly the instant after releasing the door. So for this purpose, we can write the moment equation about point O. If you assume this is the free body diagram for the door, when theta is equal to pi over 2, we have the weight and the moment exerted by the springs. The moment about point O must be equal to IO alpha. The moment is equal to 2 times by k times by pi over 2. We have 2 because we have term 2 because we have two springs, k times by pi over 2 because theta is equal to 90-degree, and k, which is calculated in previous part, minus mg times by L over 2, and this is the moment due to the weight. It must be equal to the mass moment of inertia about point O times by alpha. That in this position, we can calculate the mass moment of inertia about point O. It's similar to a rod or about a beam. You can easily calculate the mass moment of inertia about the axis passing through point O, which is 1 over 3 times by m. Sorry, I was disconnected. Can you hear me now? Is my audio clear now? Okay. So from this equation, we can substitute and calculate the alpha, the angular acceleration for this condition, and it will be equal to this time if you simplify the equation and substitute k from this part, from the part A, you substitute and you can simplify and extract the value for the angular acceleration, the instance after releasing the door from position theta is equal to pi over 2. Okay, any question? Is everything clear? If you don't have any question, we can wrap up this session. No question? Okay, thank you for your attention. And next week on Wednesday, we have the short test 2 as I announced on Moodle. Please go through the lecture notes and the examples and tutorial notes and let me know if you have any questions. And we have another lecture on next Tuesday and we will review the previous chapters. Please study. If you have any question, you can post during the lecture and we can discuss in this lecture because the chapters have been finished for this semester, and from this week we start the review of previous chapters. Okay, thank you for your attention and have a good weekend. Thank you.